All right, today we're going to be talking more about quadratic patterns. So here we have figure A is a large square. Figure B is a large square with a smaller square removed, and figure C is composed of two large squares with one smaller square added. So if our side length of the large square is 4, to find the area, remember area is length times width, so that would be 4 times 4, or we could write that as 4 squared. Okay. For area B, we have the same length, 4 and 4. So that would still be 4 squared, but we're subtracting that 1 square in the middle. That's removed. So we're going to have 4 squared minus 1. And then here we have 4 and 4. 4 and 4 on this one as well. And then we're adding 1. So we would have 2 times 4 squared. 1 for this first square, 1 for the second. And then we're adding that one little extra on the end. Okay? So that is if our side length is 4. Now, if our side length is x, we would have x and x, which would be very similarly x times x, which is x squared. Area B, we have that same x squared, but we're still removing the 1. In figure C, we still have 2 that are x squared, and we're still adding 1. So the only thing that changed is that 4 became an x. Okay? Now for our next one, our side length is 4x. So we would have 4x times 4x, which we can just write as 4x squared. We're multiplying both of those things twice, so we have to square both of them. We're going to use parentheses there. Okay. Area B is the same thing, except we're still subtracting 1. So we have 4x squared minus 1. And same thing with C. We have 2 squares that have an area of 4x squared, and then we're adding 1. Okay. And then for our last one, x plus 3, very similar to the last one because we still have more than just one number or variable there. We would have x plus 3 times x plus 3, which we could write as x plus 3 squared. And then for figure B, we have the same thing, x plus 3 squared, subtracting that one little square from the middle. Figure C, we have 2 that are x plus 3 squared, and then we're adding 1 on the end. Okay, so it's just to kind of help us visualize what's happening with these side lengths. All right. Then example 1, if the pattern continues, what will we see in steps 5 and 18? So step 1, we have 5 squares. Step 2, we have 8. Step 3, we have 13. Okay, so again, we can see we're not adding the same amount every time. First, we're adding 3, then we're adding 5. Okay, so that means we need to look and see, do we have a square anywhere? So if we look in step 2, we have a 2 by 2 square right there. And in step 3, we have a 3 by 3 in the center. In step 1, there's our 1 by 1. So that tells me that we do have n squared, right? That's matching our step number. We have a 2 by 2 square, a 3 by 3 square, and then we have 4 extra in every single pattern. Okay, so what would a step 5 picture look like? We would have a 5 by 5 square with 4 extra, okay, on the edges. And step 18, very similarly, 18 by 18 square with 4 extra on the sides. Okay, and then how many small squares would we have in each step? Well, if we have a 5 by 5 square, that means we have 5 times 5, or 5 squared, plus those 4 extra. So 5 squared gives us 25, plus 4 gives us 29 total squares. And then for 18, we would have 18 squared, plus those 4 extra. 18 squared gives us 324, plus those 4 extra, which gives us a total of 328. And then our equation, we already kind of talked about this, because we have that 4 by 4 square or that 5 by 5 square, our number of squares is found by our step number squared plus those 4 extra, okay? When you're done with this page, go ahead and go to the next one. So here we have a couple of different patterns, okay? Pattern A, the length and width grow by 1 square from step by step. And in pattern B, the number of squares doubles from each step to the next, okay? So we want to write an equation to represent the number of small squares at step N in pattern A. So because we're growing both horizontally and vertically, again, we're looking for that n by n square. So we have a 2 by 2 right here, 3 by 3 right here, and a 1 by 1 here. So that means we just have f of n equals n squared. We don't have anything added, we don't have anything taken away. Is this function linear, quadratic, or exponential? Because we have that power of 2, that is quadratic. Then if we look at pattern B, we saw that keyword that we were seeing in our exponential unit. So that doubles, right? We see that word doubling, so we could say g of n equals, we start with 1 square, it's doubling, and then our exponent is the power, okay? So because it's written in that same ab to the x form, that is exponential. Okay, so then we can go ahead and use those two equations to complete our table below. So for our first pattern, our equation was n squared. So if we look at our step number here, we would have 0 squared, which is 0, 1 squared is 1, 2 squared is 4, and we can continue down. So go ahead and complete that table and then continue playing the video after. So if we look at all these values, we can see that they're not increasing by the same amount, because from step 0 to step 1, we go up by 1, then we increase by 3, then 5, then 7 and 9. So that's not increasing by the same amount, okay? So these would not have a common difference, but they're also not multiplying by the same thing, because to get from 1 to 4, we would multiply by 4, right? But 4 times 4 doesn't give me 9, so they also don't have the same factor. And we said this was a quadratic equation. So if we look at our quadratics, if we were to take 1 minus 0, that gives us 1. 4 minus 1 gives us 3. So we're just subtracting, kind of how we found our factor for our exponentials unit, but we're just subtracting. So here, 9 minus 4 gives us 5. 16 minus 9 gives us 7. 25 minus 16 gives us 9. And we can continue this for the rest of our table. Now, again, I said they don't have a common difference, right? Because we have 1 and then 3 and 5. These numbers aren't the same, right? But if we look at what's called a second level difference, if we subtract again, we would take here 3 minus 1 is 2. 5 minus 3 is 2. 7 minus 5 is 2. 9 minus 7 is 2. And if we continue that for the rest of the table as well, you'll see that all of those are 2. So something I want you to add to your notes is quadratics have a second level common difference, okay? So that's just another way for you guys to be able to check if we have a quadratic function, okay? You can look at your pattern, you can look at your equation, you can look at the pictures, or you can look at a table and find that second level common difference. Now, if we look over to our second pattern, we have our equation here. So it's 2 to the step number. So for the first one, we'd have 2 to the 0, which is 1. 2 to the first, which is 2. 2 squared is 4. 2 cubed is 8, right? So every time we're multiplying by 2. So go ahead and finish the rest of this table as well. Pause the video and then play it when you're done. So here's what we have for our table here. And again, we said this was exponential, so these also don't have a common difference. The difference between our first two steps is 1, then we go up by 2, and then 4, and then 8, so we're not adding the same amount here. But because this is an exponential, we know that they have a common factor. That word from above that we saw, doubles, right? So if we look at our table, I can take 2 divided by 1 gives me 1. 4 divided by 2, 2 divided by 1 is not 1. Let me fix that. 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4, 2. 16 divided by 8, also 2. And that pattern continues. So these all have a common factor. So go ahead and write that at the bottom of your page or the side. Exponential, which we know from our exponentials unit, has a common factor. Okay, so again here, you can see that in looking at your table here. You can see that in looking at your equation here. Or you can see that looking at your pattern up here. So there's multiple ways for us to see what type of function do we have and how is it changing. If you have any questions, make sure to write them down and let me know.